So as I said, our brain is like dynamical systems, and of course it is stochastic. But here in Hopfield networks, we assume that it is not stochastic. And so in the Hopfield model, it is assumed that the individual units preserve their individual states until they are selected for a new update. And the selection is randomly. So when we say asynchronous, it means that we have a bunch of neurons. We just pick one of them randomly and update it. Then we pick another one, this one, and update it. Then we pick another one and update it. And so you see, it's very different from what you do in a standard way in deep learning, that you update everything synchronously. And so we lose lots of opportunities in artificial intelligence just because of this paradigm. So we don't have to be like CPU, that we have a clock. We can just pick one of these neurons and update it. And that produces infinite amount of patterns in your memory, in your brain. You have infinite amount of patterns. Each pattern is like, so each of them is 1, 0, 0, 1. So each one is a pattern. When it changes, you go to the another state. So if it is the landscape of your energy function, sometimes from this local minima, there's a noise helps you, for example, more calcium in one of the synapses. You go from one minima to the global minima, to the memory that you care most, that you appreciate more. You have learned it more, you have practiced, and you have done the recall, and you have succeeded in your recall more than other memories, because all of these local minima are just memories. But our brain tries to understand which of these local minima are more important. The one is important that is the one that is used or trained more frequently is the winner of this competition. So, the physicists have analyzed the Hopfield model. Even if you watch my playlist for graphical models, factor graph and those things, you will see we come across this Ising model. Even if in Markov chains, I've come across Ising model a lot. So, and of course, when I was electrical engineering and I was working on electromagnetics and quantum mechanics, I was again interested in these things because the concept of energy is very important. Which configuration is more probable? It's very fascinating. And because, for example, John Hopfield was a physicist, because he changed to biology, then he changed to those things because he loved physics. And he tried to use those physical paradigms, those paradigms from physics into biological networks, and that's why he is very successful. And Hopfield networks are asynchronous, as I said. You pick one of these, you update it. You pick the other one, update it. There is no single clock. So we have energy, the definition of energy. We have n units. Because you have xi, you have xj, so there is a weight between them. And if you calculate all of these combinations, you add them up. And of course, you may have an external field. For example, the external field says, for example, the hippocampus forces some neurons to be something like that. And then it is, because it is connected to neocortex, then it activates something else. So this is the external field that you can see in either electromagnetics and also in your brain. You will see this external force even in quantum mechanics. But the basic thing is that you have energy that is reduced at each time step. This is the dynamics of Hopfield. You know, when we say spin up, it means half. This is spin up, spin up, spin up. different combinations of these spins can lead to different configurations. So when we say state, it means all of them. For example, this is 1, 0, 0, 1, 0. So all of them is just one state. If we change one of them, then the state, which is this one, is changed. So the definition of state is very important. Each neuron by itself doesn't matter. The whole neurons is important. The meaning of associative memory is like this. The whole state converges to something, not just one neuron. So here we go from one energy, which is 3.5 at this state. And then, so you can represent it by the weights as well. So you go to this, after second, you go after another update, you go there until you reach this stable state that this is the memory of a cat, for example. So now we want to prove again that it converges, just like the BAM model that we proved. So the energy function, we write it and we just changed one of the bits of this state. And then you will see that the difference between the energies is like this. If you simplify that, you will see that this is the total energy, the difference of energy if we just change one of the bits. And you will see that E of x prime energy after we change one of the bits. So the energy of that is reduced. And as I said, consider a Lyapunov function in nonlinear dynamical systems. The energy function, if it is reduced, then it reaches the global minimum, for example. But here in Hopfield networks, as I said, we reached some local minima, which is not good. So this is one of the limitations of Hopfield networks. That's why we try to generalize it with a general Boltzmann machine. We try to generalize it with spiking asynchronous neural networks and many other models in computational neuroscience. So the Hebbian learning, Hebbian rule, when I remember Hebbian word, when somebody says Hebbian, I say neurons that fire together eventually wire together. This is inside in my brain. So my brain has associated Hebbian, the word Hebbian, with this quote. And so, for example, if these are fired together, both of them are one, then eventually they become, so eventually the weight of that is increased. So the delta of the weights, the increase of the weights is just xi, xj. So if xi is 1, xj is 1, delta w is 1, so it is increased. But if one of them is 0, either 0, 1 or 1, 0, then this one becomes 0. It means that it will not be updated. It's just the same thing, and it does not change. So in Hebbian learning, we can show that if we take this law, let's say it's a very simple law that is implemented biologically very simply, and we understand it. If we just do that, we show that X1 is a stable set of the network, stable state of the network. So application of that for Hopfield networks, we can use it for traveling salesman problem that I've explained in my playlist, an approximation algorithm. But here, if we just use the problem of 8 rooks puzzle, then we have 5,000 combinations. But you should use other tricks in computer science, such as backtracking. But the one that I want to explain here is just using Hopfield networks. Because you know that we want this energy to be minimized. We don't want all the rooks to be in one line, in one row, or in one column. Not in one row, not in one column. So this is the total energy that should be reduced. And if you reduce it, the states converge to the solution of 8 rooks puzzle. The same for 8 queens. We have a different energy function as well. So there are, for example, 92 solutions. It means that it has 92 local minima. It has 92 local minima. And some of them, and all of them, of course, have the same merits. All of them have the same merits.